So, I mean, we've had so far today and quite a number of amazing talks, but hey, don't run away yet. We still got one more to come, and this one is going to be very, very impressive. So, Yiheng Lin is going to talk to us about quantum entanglement between an atomic ion and a molecular ion. This is going to be a video, so please take it away, and we will come back for question and answers after it. Thank you very much. Please.
Hello everyone, my name is Yiheng Lin. I'm from the University of Science and Technology of China. First, let me thank the organizer for inviting me. I'm going to talk about our recent work on creating quantum entanglement between an atomic ion and a molecular ion. This work is jointly done between NIST and USTC, and we performed the experiment together at the setup at NIST while I was visiting there. Here we are interested in the physics of molecules. After cooling down molecular translation motion, and the laser spectroscopy can be done with negligible Doppler shifts or broadenings, and one can precisely measure the vibrational and rotational transitions. These transition frequencies can vary in a wide range, all the way from degenerate for rotational sublevels to infrared and to optical frequencies for vibrational overtones. So these are quite unique compared to atoms. And on top of that, we also have electronic orbits, electronic spin, and nuclear spin, similar to atoms. Precision metrology of molecular transitions can be used as a probe for fundamental constants. People also study the bonding physics about how atoms form the molecules, and interactions can occur between different molecules, for example, cold chemistry, and interactions between molecules with other objects such as atoms, superconducting qubits, microwave photons, etc. Recently, there are also proposals on applications using molecules in quantum simulation and even quantum computing. I would like to also invite you to other talks in this conference with Zip Nair, Kan-Kun Lee, and Jun Ye. There are also a number of very different platforms for cold molecules. For neutral cases, one can start from atomic Bose-Einstein condensate and make cold molecules in pure states and load them into optical lattice for further study. One can also assemble molecules from single atoms trapped in optical tweezers. And similar to atoms, one can find closed cycle transitions in molecules and can directly cool them down to below Doppler temperatures. And for this work, KRB molecules go through cold chemistry processes. Here I'm only naming a few of these experiments, and many other interesting experiments have been done for other types of molecules, or even beyond diatomic molecules. Another case is that if one or more electrons in the molecule are knocked out, then they become charged. In those cases, they can be trapped in an ion trap. Interestingly, atomic ions can be co-trapped, and they can have Coulomb interaction with the molecules. Thus, by laser cooling the atom, the molecules can be sympathetically cooled. And as we will mention later in this talk, we can even use the atom to indirectly project or manipulate the states of the molecule. These techniques have been developed for quite a while and have been used in many cases. For example, using HD plus molecule as a test upon quantum electrodynamics and can probe fundamental constants, or non-destructive measurement of molecular rotational spectra. Again, here I'm only naming a few of these experiments, and many other interesting experiments have been done. Here, the platform we use is calcium ion and calcium hydride molecular ions. For calcium atom is quite popular in the trapped ion community. It has closed cycle transitions. For readout, has near perfect state preparation and manipulation. And so Doppler cooling, EIT cooling, and sideband cooling for the entire ion chain of motion. So here for the motion, what we meant is that for charged particles in the same trap, the motions are coupled. For example, they can vibrate in the stretch motional mode, where the particles oscillate out of phase. And here in our experiment, this mode has a frequency of 5.16 MHz. After ground state cooling, we use this mode as a bus to couple the atom and the molecule. This is the key technique in our work. Another reason why we use this molecule is that with 2 calcium ions in the trap, we can leak in hydrogen gas to form the molecule in situ, while the molecule is being cooled by the atom. So here our setup is at room temperature. So a molecule is automatically in the electronic ground state, and also in its vibrational ground state. So here we're interested in the rotational states. Here we use the quantum number J to label the rotational manifolds, and the typical energy splitting corresponds to a frequency of few hundred gigahertz to terahertz range. And each of these manifolds has 2J plus 1 different rotational sublevels. And because the hydrogen proton, the proton has a nuclear spin of 1/2, all the levels are doubled. So here we face a challenge. So because all these levels have populations, there are around 1% or even less population in each of these sublevels at room temperature, and there are a large number of them, and the frequency span between different rotational manifolds is on the order of a terahertz, so it's quite large. It's out of reach for AOMs or EOMs, and obviously there are also no easy cyclone change available for the molecule. So here our solution is that we identify unique transitions for different J manifolds, and we use the atom to perform quantum logic readout, projection, or pumping to manipulate the molecule. And here for the molecule transition, we use stimulated Raman transition for that. Here we apply a magnetic field with 0.36 millitesla, and for J equals to 1, we can realize that there's a 10 kilohertz transition between these two levels, while the other levels have a really close level splitting, and the other level has lower in frequency. For J equals to 2, then this particular transition is different. It's 13 kilohertz instead of 10 kilohertz. So this very transition can be used as a signature transition to identify different rotational manifolds. And for quantum logic spectroscopy, basically we can transfer the information between the atom and the molecule so that we can use the atom to probe the states for the molecule. In particular, what we use is the motional states. Because it's collected between the ion chain, then we can cool it down to the ground state to begin with. Then if the molecule is in the excited state, we can perform the so-called molecular sideband transition, where it de-excites the molecule and put the excitation in the motional mode. Then we can use the atomic sideband to transfer the motional excitation to the atomic state. Then we can read out the atomic state and infer whether the molecule was excited or not before. And also you can notice in this process, the molecule was projected. So this can be used as a way to project the molecule. Another type of manipulation we can use is that after the transfer of molecular excitation to the motion, then we can do the cooling with the atom. Then from this state to here, this forms a closed cycle of pumping for the molecule. So we can choose different pair of molecular levels and perform this type of pumping and accumulate the populations. So here to manipulate the molecule, what we use is a stimulated Raman transition, and we use an infrared laser, split the laser into two paths, and use AOMs to control the frequency difference. If we tune the frequency difference to match with the energy difference of the rotational sublevels plus the motional frequency difference, then we can use the third level as with the electronic upper state to drive the so-called stimulated Raman transition to change the state of the molecule while adding or subtracting one quantum of motion in the entire ion chain. So this technique is suitable for a wide range of molecules because this detuning is really, really large. So for many different molecules, then this laser is suitable. And also we don't need to know exactly the transition between the ground state to the upper electronic excited state. The downside for this technique is that this tuning range is quite limited. For our experiment, we can use AOMs to tune the frequency. And for other experiments, for example, one can use EOMs to go up to a few gigahertz in frequencies. But this cannot reach the gap between different rotational manifolds, which is on the order of few hundred gigahertz or even terahertz. So on those cases, we use instead optical frequency comb, which is a femtosecond high-sap laser. There, we again split the laser into two paths and use AOMs to tune the frequency. But here, because there are many different comb teeth for the comb, and any pair between these two paths, if they match with the transition frequency, they can drive the transition. So because the repetition rate is 80 megahertz, which is the splitting between adjacent teeth, then we can use AOM to bridge the gap. So with this, one can drive near degenerate transitions all the way to terahertz in transition frequencies. And in previous work, people have demonstrated 1.8 terahertz transition in calcium atom with this frequency comb technique. So with all these tools, we can start our experiment. First, we do the optical pumping to accumulate populations to certain states. And after this process, we can try to probe the frequencies for the transitions. And we can clearly notify, we can notice then we have 10 kHz for J equals to 1, 13 kHz for J equals to 2, etc. So these signature transitions are visible. But because there are still many different rotational levels, we need to project and herald for each single event. So what we're doing is that we try out the signature transition. And if this transition successfully drive the population for the molecule from here to here, then we obtain a motional excitation. Then after measuring from the atom whether there's a motional excitation or not, then we can project the molecule into certain rotational level. So with this, then each single shot we perform this projection, and we can know where the molecule is and start our experiment accordingly. So after this being done, then the molecule really behaves like an atom, and we can drive transition and see spectrum. We can do Rabi flopping, and we can also do Ramsey experiments. So here we are doing a 15 millisecond Ramsey time, and you can see that the contrast is still quite good for the molecule. Further information can be found in this reference for previous work. And with the help of optical frequency comb, we can also drive transition between different manifolds. So this experiment, we can see disappear of population in J equals to 2 and appearance in J equals to 4. And then we can do Rabi flopping between these two manifolds. So further information can be found in this paper, in our recent work. And also probing different transition frequencies, one can back out the rotational constants. So for this rotational constants, comparing to the theoretical result, they match quite well. And the precision is really, really good. So with all these tools at hand, then it's time for molecules to reach out to couple to atoms. And we try to demonstrate a technique which is potentially suitable to reach to other systems. And here we have a long sort of milestone to perform quantum entanglement between the atom and the molecule and quantitatively see how good is the entanglement. And because there are many different transition frequencies in the molecule, then we would like to repeat this entanglement between the molecule and the atom while choosing different molecular qubit frequencies. So what we do first is that in J equals to 2 rotational manifold, we choose this 13 kHz transition and label these levels as qubits, spin up and spin down. And what we can do is to drive transition between these two spin up and down states using the infrared laser, and also we can tune the laser to the blue sideband or the sideband transition to drive a transition while we are driving a excitation for the motion. And further, we can also turn on the optical frequency comb to drive between this level in J equals to 2 all the way to J equals to 0 in another level. For the atom, we label the ground state using S as the ground state, and we label this another state in the excited state, which is a metastable state, D state. And between the ground state and the excited state from the atom, we can use the 729 nanometer laser to drive either the carrier or the sideband. So with this, we can create an entanglement between the atom and the molecule. So the process is kind of complicated, but what we can do is that we can prepare the atom and the molecule in the ground state, and then cool the entire chain also to the motional ground state to begin with. Then we can drive half a atomic sideband transition and create a superposition between the original state and the excited state of the atom and the excited state of the motion. So this is already a entangled state between the atom and the motion. And after that, what we do is easy. We transfer this motion excitation to the molecule. With this, then we can create a belt-like state with both atom and molecule de-excited, or they're both excited. So mathematically, we use S spin up plus a phase times D spin down to label the entangled state. And further, to quantify the entanglement, we can measure the populations for each of these components and see their correlations. And also further apply, repeat the experiment and further apply pi/2 poles on both the atom and the molecule, which is somewhat like an interference experiment between these two components, and we can see whether they are really phase coherent. And by varying the phase, then we can see something like this. So this is the so-called parity plot. If we vary the pi/2 phase, we can see a contrast change. So at the end, we can measure this contrast and combine with the population, we can back out a fidelity. So here for the 13 kHz qubit, you create a fidelity of 0.87 for this entangled state, which is above the 0.5 threshold. And we can repeat this experiment and by mapping the entanglement from the J equals to 2 level to J equals to 0 and label this instead as spin up and down, then we can create an atom-molecule entanglement. And we use a similar technique to measure the fidelity. And in this time, the fidelity is somewhat lower. We get a 0.76 fidelity. But in this case, this is using the molecular qubit with a frequency of 855 gigahertz, which is 7 orders of magnitude higher than the previous low-frequency qubit. So with this, we have fulfilled our milestone, created an entanglement with different choice of molecular qubits. So this fidelity is limited by the laser coherence of the 729 nanometer laser and the optical frequency comb. And also it's limited by the magnetic field fluctuations. The next step is that we can either repeat the experiment in the cryogenic environment so that the population is less spread across the molecule and also expand to more particles. So I must acknowledge the contribution of the experimental setup at NIST. So this is the setup, and we're showing a whole bunch of lasers across different directions to do the manipulation. And also I need to thank the collaborators at NIST, particularly Dave Librand, Christoph Kurz, James Chow, Dave Hume, Didier Libri, and Philip Perschel at KIT at Germany for theoretical help for the COM spectroscopy. And also here we are setting up a trap ion experiment at USTC. So we have openings for postdocs and graduate students. So this is our website and this is my email. If you are interested, feel free to contact us. Thank you for your attention.
Very, very nice talk. It's beautiful to see hybrid systems between atoms and molecules. Really impressive. So, I mean, so far we have 2 questions, and the first one you kind of hinted at the end that if you go to cryogenic temperatures 4K, how much are things going to improve? I mean, so what do you expect your populations to go down to at 4K? All those type of temperatures.
Can you guys hear me? Is the network okay? Okay. Yeah, so actually it will pose opportunity and challenge at the same time, I think. So at a lower temperature, we may not even have to go all the way to 4K, maybe slightly lower in temperature. That will make the molecule lifetime much longer because there are black body radiations that will shuffle the population around. So with the lower temperature, then the molecule is stuck in a certain level of rotation, then it may be better. But on the other hand, if we don't know where the molecule was to begin with, then it gets stuck. So we have to scan through all the transitions to find it. But once it was found, then we can start experiment. Also, at lower temperature, particularly below 10K, then the vacuum is much better. So the lifetime for the ion molecule system will be much improved. So that will make the experiment nicer as well.
So that kind of leads to the next question from our audience. Can the entangled state that you've produced have a memory effect and carry information, and how?
Do you mean by carry information for the entangled state?
Yes, or can you store information on the entangled state?
Absolutely, yeah. That's what the entanglement is for, I guess, right?
Yeah, exactly. This was one of the questions from the audience, from one of the people in the audience. So maybe you want to explain kind of how you would do it.
Oh, so it behaves just like a normal atom does, I would say. Like for information, you can actually the best way. The thing we are doing now is just entanglement demonstration. But what may be more useful in the future is to do a quantum logic gate between the atom or molecule, between molecules. So that can be much more useful, I think. But actually, what we were doing already is some sort of a quantum logic gate. It was similar to the original Dirac-Solar architecture, but it's simplified for this particular state generation. And furthermore, other types of ion gates can be implemented between the atom and the molecule. So with that respect, then it can be fully functioned as a quantum logic or quantum information platform, just like what other things are doing. So, yeah.
Yep. So, I mean, I have a question myself, given part of my background. So at the moment, I mean, it seems very clear that you're entangled, but have you thought about using, I mean, your fidelity indicates that, but fidelity is not an entanglement witness in a sense. So have you thought about doing full state tomography, reconstructing the density matrix, calculating the degree of entanglement, or using one of the Bell state entanglement witnesses that are available to give, I don't want to use the word conclusive, but to be more definitive that it's entangled rather than inferred?
Yeah, exactly. Yeah, like doing a CHSH would be much better, I think. But actually, the problem is that you can see on our paper, I personally don't 100% like the statistics because the experiment was slow. if the experiment can be much faster, then I will be happy to do all sorts of tomography or other things. So in the future, if the experiment repetition rate can be much faster, then we can look for all those measurements much more than just observation. So right now we're just doing an observable for the entangled state, but we can do much more, I agree, yes.
So actually, you set your next question up. So how do you improve your rate? How do you make it faster? And what are the limits?
Yes. So the rate is actually limited to some extent. The chance of finding the molecule in a particular state that will take some time because it's heralded, and we have to wait for the back body radiation to shuffle around to the particular state we are waiting for. And the second thing is like it also will kill the molecule state after some time. So the answer is already there. If we cool down the chamber, reduce the black body radiation, that will help a lot and make it really behave by an atom. So that we don't have to herald so much. We just go ahead and do the experiment in the normal way. That may be one way. Another thing is maybe another molecule may be better. The molecule we choose, as I was saying in the talk, is just for convenience of the experiment.
Okay.
So maybe there's a much better molecule waiting, and even for post.
So you're leading again to a question that comes from our audience. So given where you are at the moment here now, if you use other molecules or improvements, do you think you can generate this entanglement at room temperature?
For certain molecules, yes, I would say, because here we're relying on the fact that we can do quantum logic spectroscopy, meaning that we have to somehow know where the molecule is. Like we have the signature transition available. So that would be the priority. So if other molecules, if you choose a random one, it doesn't have this kind of signature transition, that would be tough to do. But for a lot of molecules, I think this technique is available. Then we can find particular molecules that maybe have cycling transitions. Then it already behave like a qubit to begin with. We can even cool down and create pure state to begin with. Don't have to do the quantum logic.
Yeah, I mean, I see great promise given that this hybrid system of atoms and molecules. So, I mean, I really look forward to seeing the results come out as your lab continues this establishment over there. So, given the time, let me thank you again for your presentation today. I mean, I learned a lot from it because I did not know it had moved that you got that far advanced. So, thank you very much. And then I'll just make one or two final remarks to all our invited and plenary speakers today. You've given an awesome session here, okay? The session has been really, really powerful. I mean, I think we've learned a lot, but there is a take-home message. The conference is not finished. The session may be wrapping up in 30 seconds, but there's another session on quantum communication starting just afterwards. And then later in the morning or evening, depending on your time zone, we have another invited session coming ahead. So please come to it, enjoy yourself, ask questions, and learn a lot. Thank you very much. Please enjoy yourselves.